All right, good morning. Hope we all had a good weekend. Hope we had a good productive weekend. Couple of reminders as well as a notification that I did post your review for test 2 on chapter 6 in my math lab as a homework assignment. Now, it's listed under homework, although it's not actually going to count as a homework grade. That grade is muted from your average, just so you know. So it's like me handing you a paper review in class, except now you'll actually have my math lab to tell you whether your answers are right or wrong. I believe there's about 25 questions in that, maybe 24, maybe 26, somewhere in that ballpark. But the test itself is only going to have 15 or 16 questions. I have 15 up here. I think it's 15, but it could be 16. So again, the review is a little longer than the test this time, and I did it that way because you actually get some feedback on your answers. And the test, I'm not pulling anything out of thin air. All the material on the review is what the test itself covers, so there shouldn't be any surprises. Now, remember that you are going to get 2 attempts, and excuse me, you do get 2 attempts, and I'm only going to count the highest grade. I'm not averaging the 2. I'm not grading the one that happened second. It's automatically set up to take whichever one you did best on. So remember that test is due by Friday, 11:59 p.m., and the homework for the chapter is due Thursday. So the homework is due a day earlier. And unfortunately, right now, my math lab was doing some system maintenance all day yesterday, and they must have just gone a little over time or messed something up in the process. I have not been able to get on my math lab this morning. I can sign in, but when I try to get to any homework, grade book, anything like that, it's giving me errors. When this happens, it's usually no more than a few hours or half a day at most. So hopefully this will not affect us. If for some reason this drags on till tomorrow, then we might have to, do an extension or something like that, but I'm not saying that yet. I'm under the assumption that things will go well, ha ha ha, and that we will be perfectly fine with all the due dates as they are. So again, this is an excellent point to remind us not to wait to the last second to do things, because online systems go down occasionally. So as soon as you have the opportunity, work on your homework, work on your reviews, work on your tests. All right. So with that being said, we are going to move on to new material. We did close out chapter 6 last time with those trigonometric equations. We took almost 2 full lectures to do a whole boatload of examples of that stuff. So hopefully there'll be enough to help you with your homework, review, test, and ultimately the final exam. Okay, so let's move on to chapter 7, and 7.1 is the law of sines. So I'm going to do a little bit of typing here and there today up here just to make things a little easier. The law of sines. The law of sines, I feel like we've probably talked about that before, right? Well, no, actually. you see the law and you see the word sines. Oh, we've talked about sines a lot, and we've talked about some laws and properties, but we've never actually dealt with the law of sines, and we're getting into a whole new world now. This chapter is dedicated to triangles that are no longer right. So we will now deal with triangles that are not, and I'm putting in quotes, right, as in having a 90-degree triangle. These are also known as oblique triangles. So an oblique triangle is one that does not have a 90-degree angle. So again, every triangle that we have dealt with in this course up until this moment has been a right triangle. There has been an angle that was exactly 90 degrees. In this chapter, we are going to deal with every other case. We're going to deal with cases where the triangle has angles of maybe, I don't know, 10 degrees, 20 degrees, and then 150 degrees. So none of those would be a right angle. Now, when you're dealing with oblique triangles, there are two cases, and we don't necessarily need to worry about this that much, but it does have implications. All three angles are acute, which means less than 90, or one angle is obtuse, which means greater than 90, and the other two are acute, which again is less than 90. There's no way we can have two obtuse angles in a triangle, because an obtuse angle is a minimum of 90.0000001. So let's just say the smallest obtuse angle is a whole number of 91 degrees. If you have two angles of 91, that's 182. That's not a triangle. There's no way you could have a third angle be -2 degrees. All angles are positive when we're dealing with geometric figures. So when dealing with these oblique triangles, you must avoid spelling properly. You must avoid the Pythagorean theorem. The Pythagorean theorem is only for right triangles. A squared plus b squared equals c squared is only when c is a hypotenuse, and hypotenuse means it's opposite of a 90-degree angle. So we are no longer in this chapter going to be dealing with the Pythagorean theorem to fill out pieces of a triangle. So we'll have to have some other methods, one of which being the law of sines. So we can fill in all 6 pieces of info, aka angles and sides, if we're given 3 components. One of which must be a side. So when we were trying to find information about triangles in the past, we always had 3 pieces of information, 2 sides and an angle, or 2 angles and a side, something like that, for those right triangles. And we were always able to figure out the rest by using Pythagorean and then SOHCAHTOA pretty much. And we can still find all the information given half of it. So if there's 6 pieces of info for a triangle, we need half of it. But this one little issue is critical. One of them has to be a side. One of them has to be a side. And this is because of what we call similar triangles. So let me pull up a whiteboard. So let's say I gave you just 3 angles. So let's say I told you that these angles were, I don't know, 50, 60, and 70. And I'm not drawing this to scale. Please don't say, oh, hey, this looks like the biggest angle, but it's the smallest number. That's not the point here. Let's just say I gave you these 3 angles. Sorry, somebody's making noise outside of my building. I gave you these 3 angles, and then, well, what can we really do with this? Because of something known as similar triangles, I can draw one a lot bigger. Now, again, please pretend that these angles are exactly the same. 50, 60, and I should really put degrees on all of these. We'll go back and do that. There we go. So here's a triangle with 50, 60, and 70 as the 3 angles. Here's a triangle with 50, 60, and 70 with the 3 angles. If I give you the 3 angles, you have no idea how long these are because of similar triangles. Similar triangles just means that the 3 angles are the same, and that the ratio between this top right side and this top right side would be the same as this top left side and this top left side. But if I don't ever give you any of these sides, you can't figure any of them out. These are completely intangible to have one number because there's actually infinitely many solutions. I could draw this triangle super teeny, and again, pretend that I just drew it the exact same way. So that's 60, this is 70, and this is 50. So by giving you 3 angles, there's no way you can determine any of the sides because you could draw it teeny, you could draw it medium, you can draw it large, extra large, however you want to do it. All right. So we have to be given at least one side, and it's actually really nice when they only give us one side. So they're either going to give us one side or two sides in general. They can give us all three sides. That'll be in the next section. We'll save that for another day. So the two easiest cases, let me say easier cases, are ASA and SAA. Now, A stands for angle, and S stands for side. So when I say ASA, I'm saying I've given you two angles and a side in that order as you go around the triangle. So if you see your first angle that's known, if you were to say move clockwise or counterclockwise, it doesn't technically matter. The next thing you get is a side, and then the next thing you get is an angle. Or if the first thing you look at is a side, the next two pieces of information you would see going either clockwise or counterclockwise would be angles. And really, you don't have to worry about how we write ASA or SAA. That's not the point of any of this. It's just the fact that there are two angles and a side. Let me put that here. Two angles and a side. This is the easiest case for many reasons, which we're going to wait until we kind of see when we're not an easy case to go into that. These will always have one solution. And by one solution, I mean side A, side B, side C, angle A, B, and C. There's only one unique value for each. What I'm hinting at here is that there are cases that have more or less than one solution, but never when we're given two of the three angles. If we're given two of the three angles, it's always one solution. It's always the easiest type of problem. So how do we go about finding this information? Well, first, find the third angle by using 180 minus the first minus the second. By 180, I mean degrees, equals the third. That's just using the fact that the sum of the interior angles of a triangle is 180 degrees. We've used this fact many, many times. Then use the law of sines to find the remaining two sides. What is the law of sines? We haven't said it yet. We'll put it on the whiteboard in just a minute. Give you a few seconds to write that. And remember, if I ever don't leave something on the screen long enough, you can always go back to the YouTube file and use pause. It's kind of wonderful that these are all getting recorded now. Pros and cons. All right, so the law of sines, and this is a really critical law. And it's one that we're not going to do the proof of. The proof would take us a really long time. So I would suggest you to check it out on your textbook or go to the internet if you are interested in proofs. If you're really going to go far in math, proofs are always a good thing to check out. And we do some in here. We do the ones we have time for. All right. Excuse me. Oops, wrong button. All right, so the law of sines. So let's say for a triangle, and it might look like I'm drawing an equilateral triangle here. Please do not assume that this is an equilateral triangle. With angles A, B, and C, and then sides of A, B, and C. So this is an uppercase C in the top, an uppercase A and an uppercase B. So we use uppercase letters for angles. Give me 1 second. So we use uppercase letters for angles, and we use lowercase letters for the side lengths. Now you'll also see me use Greek letters as well, alpha, beta, and gamma. So those are the equivalent. So just kind of or alpha, beta, gamma, A, B, C. So sometimes we'll use uppercase letters to represent angles. Sometimes we'll use Greek letters to represent the angles. It just depends on what the textbook or my math lab or teacher decides to use at any given time. So those letters, the little fish looking one is alpha. If we haven't said in class before, it's been a minute. The B with an extra extended bottom on the back is what we call beta. I know we've talked about these in class before, at least alpha and beta. And then if you take the fish and rotate it 90 degrees, that's what we call gamma. Those are our A, B, and C, if you will, of the Greek alphabet. All right, so for our law of signs, and I'll write it both ways. Little a over sine of big A is equal to little b over sine of big B is equal to, that's weird, right? Little c over sine of big C. This is the law of signs. Oops, that button always gets me. Or if you have it in Greek, then it would be little a over sine of alpha is equal to little b over sine of beta is equal to little c over sine of gamma. So again, these are the same two bits of information, just different letters, different American versus Greek letters. Me personally, I prefer the right version, and some of you might be able to guess why. Upper and lower and lowercase c's look pretty much the same. You have to exaggerate them. So I am a bigger fan of using the Greek letters. However, I do blended problems. I'll do some with regular letters, some with Greek. So you have to be used to seeing both of them. Now, again, this is kind of a weird looking equation or law, if you will, because it's got 3 bits. We usually only see, something equal to something. So this looks like a proportion if you ignore all the C stuff, if you just look at the first bits. Or if you look at the middle and the right, it looks like a proportion. Or even if you cut out the middleman, if you use just the A's and C's, so this one equal to this one, that would also be a proportion. And we solve proportions by cross multiplying. So what we will generally do is we will ignore, or let me just say we'll only use 2 of the 3 sides at a time. And by sides, I mean of the equation. I'll say of the law. At a time. I changed my tense. So we'll only use the A's and the B's, or we'll only use the B's and the C's, or we'll only use the A's and the C's. You pick the 2 out of 3, and you pick the ones that are most convenient. So that is our law of signs that we are supposed to memorize. I would never put this on a formula sheet for you. Never, ever, 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 because it's honestly a pretty simple formula. It just says that a side length over the sine of its angle is equal to, pick another pair of information, and it's the same thing, side length over sine of angle, side length over sine of angle. In fact, you can flip every single one of these upside down and call this the law upside down. So sine of A over A equals sine of B over B. But you have to have the angles inside of the sine. You have to have the side lengths not inside of a sine. Okay, so enough discussion. Let's try this out. Example 1. Oops, I'm on text still. And I believe this will be A. Yes, it is. Find all missing info. And let's say that capital A, or alpha, is 56 degrees. Let's say capital C is equal to 24 degrees. And then lowercase a is going to be 22. Now, the angle always has to be opposite of the side linked with the same letter. So little a being 22 says the angle opposite of that, excuse me for that writing, has to be 56 degrees. So if you wanted to draw up a triangle for this, which you do not have to, again, you don't have to have the triangle. And again, I'm kind of drawing it, it looks equilateral. It's not what I'm necessarily saying. So if I make this the A, that the 56 degrees, that means this side has to be the 22. Now, it doesn't matter what letter you call this top angle or this other angle. We know that we have one of them is 24 degrees. You can make the top one the 24, or you can make the right one the 24. It does not technically matter. This looks a little smaller, so I'll make that the 24 degrees. Which means that this side up here, if this is our angle C, then the side opposite has to be the length C. That's a lowercase c. This top angle is the missing one, the one that's unknown, so that's our angle B, meaning that the side opposite has to be the letter B, lowercase b. And again, in terms of the math, I could have put angle C here in the top, which would have put angle B in the bottom right, and the C and the B would just swap locations. The numbers are going to turn out to be the same no matter what. And that's because of that three-sided equation. It's just that the ratio of the side lengths to the sine of the angles is the same for each opposite pair of information. Okay, so the first thing we said to do if we're given two of the angles is to find the third angle. That's the easiest thing to do because we know that the three have to add up to 180. And you don't have to write 180 minus the first minus the second. You can actually just say that angle A, which is 56 degrees, plus angle B, which is the unknown, plus angle C, which was 24 degrees, has to equal to 180 degrees. You can go ahead and say 180 minus the two angles, or you can just have them written out in the standard equation. It does not matter. All right, 56 plus 24, that's going to be 60, 70, 80. So that's 80 degrees plus B. Could have put the B first, doesn't matter. Equals 180 degrees. We're then going to subtract 80 on both sides. Which will give us B is equal to 100 degrees. So this top angle, as we decided to draw it that way, is 100 degrees. We now have the three angles. That's 4 of the 6 pieces of information. Again, each triangle has 6 bits of information. You have to be given 3 to find the other 3. Now we're going to use the law of sines, abbreviating LOS as law of sines, to find the next 2 sides. So that was little a over sine of big A equals little b over sine of big B equals little c over sine of big C. Again, same thing we wrote before. You must use a completed pair. In this three-sided equality, we're only going to use 2. We're only going to use the A's and the B's, or the B's and the C's, or the A's and the C's. But we have to pick a pair that's completed, otherwise we're going to have 2 unknowns instead of just 1 unknown. So let's see, what do we actually have all of? We have side A, and we have angle A. So A is the completed pair. We have angle B now at 100 degrees, but we don't know its side. We have angle C, but not its side. So the completed pair in this problem are the A's. So that means we have to use little a over sine of big A. So 22 over the sine of 56 degrees, that is a 5. We have to use that pair. Now, we can go after the B's first, or we can go after the C's first. That does not matter. Okay. Well, B comes before C, so let's attack the B's first. Again, doesn't really matter. So we're going to go after B. So side B over sine of angle B. And we said that angle B was 100 degrees. Now, what we have to do here is solve for little b. And this is a proportion. And generally, the easiest thing to start out with proportions is to cross multiply. We don't always have to do this. We can have more advanced. Did I spell that right? Multiply. Yes, I did. Sorry, I was talking at the same time. We don't actually have to cross multiply to solve this. That's going to take us 2 steps to solve. I could solve this in 1 step, and I will explain that because it's a shortcut that I find most people want to take ultimately. But again, we're after b. This is what we want to solve for. We're trying to solve for this guy right here. So cross multiplying will give us 22 times the sine of 100 degrees is equal to b times the sine of 56 degrees. Again, I'm just kind of circling the thing we're solving for. You don't have to do this. This is an old algebra trick. When things are looking crazy, it's just a helpful reminder. That's what we're trying to get by itself. So to get rid of everything next to it, that's b times the sine of 56 degrees, we're going to divide both sides by the sine of 56 degrees. Okay, so what that tells us, or what that gives us, on the right side, the sine of 56's will cancel. And you might say, well, why haven't we, drawn up a triangle to figure out what sine of 100 or sine of 56 is? Because we don't know how. We know how to do that for angles like 30 and 45 and 60, and then any multiple of 90. We also know how to do that for some half angle and double angles now, like 15. But we don't know how to do this for pretty much every angle in the world. We would need a calculator for this. And in fact, I'm realizing that I goofed. I meant to download a TI-83 app, and I did not. So I'm not going to be able to show these calculations on the screen, but I do have the numbers. I will make sure I have that calculator downloaded next time. I don't have a document camera at my house, so there's no way for me to actually show you what's happening on my calculator. All right. So what this gives us is 22. Oh, let me switch my color back to black. 22 times the sine of 100 degrees over the sine of 56 degrees. That's equal to the b. Now, if I give you a no calculator test, this would be the answer for b. You couldn't take this any further without a calculator. Again, you could not take this further without a calculator. However, this would be the first test where I would, quote, allow you to use calculators. I know with a take-home test, that's a little difficult to enforce your test too, so just be as honest as you can. But if we were in class traditionally, this is where we start saying, oh, well, we want a number for this, so let's be able to type that in. Now, in your calculators, make sure you're closing your parentheses when it opens a sine of 100 degrees. Make sure you're closing it. I just want to show you what it would look like if you type this in your calculator. It would be 22 times the sine, and then it would open a parentheses automatically. You type 100, you got to make sure you're in degrees, and then you'll go divided by the sine of 56 degrees. And again, you would have that 56 in parentheses, make sure you close it. And when you go through and do that work, if you round to 1 decimal place, you'll find that b is 26.1. So again, I rounded to 1 decimal place. That is generally what I am looking for, but you have to pay attention to what my math lab wants. It may say round to the nearest whole, it may say round to the nearest 100th, it may say round to the nearest 10th, which is what we just did, 10th. So again, please pay attention to the directions. It is going to break your heart if they tell you to round to 1 decimal, but you round to 2 and then they mark it wrong. All right, so we have our b, and let's box up answers. So here's our b for the side. Here's our b for the angle. So that's now completed. So in fact, when we go to find side C, we could actually use the b's to find side C, but you're not going to see me do that. I always like to go with the original pair that was given. That way, in case I mess this up, then I won't have messed C up in the process. or maybe I rounded inappropriately or just too much for the context of the problem, and that might make C be just a little off, because when you use rounded numbers to find other information, that calls error truncation. So I just said the wrong word, didn't I? I said truncation. I meant to say propagation. I was stuck on that. Error propagation. All right, so now let's find the C's. I'm just going to do this. It's not saying a new example, just a new version of the law of sines. Let's still use the A's. So 22 over the sine of 56 degrees. Again, that's the completed pair of A information as you see up here. And now instead of saying it equal to B's, we're going to go C's. So little c, which is the unknown, over the sine of angle C, and angle C was 24 degrees. So again, we can cross multiply, Cm for cross multiply, which will give us 22 sine of 24 degrees is equal to C times the sine of 56 degrees. We're trying to solve for that C. Again, you don't have to do this. This is just something I do with my Algebra 1 students generally. That's what we're solving for, which means we have to divide both sides by the thing next to it, which is the sine of 56 degrees. So therefore, C is equal to 22 sine of 24 degrees over sine of 56 degrees. That's our C. And again, I could make this a no calculator test and that would be the answer. It's not pretty, but it's analytic. But we are supposed to put this information in a calculator, make sure you're closing the parentheses for the 24 and the 56 so that you're not putting a sign inside of another sign. That would be really weird, and it tends to lead to no solution in a calculator, undefined, error, whatever. Make sure your calculators are in degree mode, and what you should get, rounded to 1 decimal, is that C is 10.8. Now, I never described the units as inches or meters or miles or yards or anything, so there's no units in these links, but they certainly could be units. So now we have the completed pair of information for the C's, and we are done with this problem. I did not have to find the B's before the C. I could have found the C, then found the B. The order that you find these two sides doesn't matter because they don't affect each other. I find this one, I can find this one without having done B. I can find this one without having done C. But you do really need to find the angle first. Asterisks, you could have found this second, but you'd have to do this proportion first, this cross multiplication first, then you'd go back and find the B's after you find the angle. But you really should just go ahead and find the third angle first because it's by far the easiest thing to do. Before I do the next example, I want to show you that shortcut I mentioned. I said up here that we cross multiply, and then after we cross multiplied, we have to divide. But really though, because this is B over the sine of 100 degrees, this is B over a number, all you have to do is get rid of the sine of 100 by multiplying both sides by it. So let me show you on the next page an alternate version of this. So, and I'll only do for the B's. We had 22 over the sine of 56 degrees is equal to B over sine of 100 degrees. So let's just, again, take a shortcut and multiply both sides by sine of 100 degrees. Instead of cross multiplying, I'm just gonna multiply both sides by the sine of 100 because that's B divided by a number. To get rid of dividing by a number, you multiply by it. So on the right side, all the complicated mess is gone. And now we get sine of 100 times 22 is the same thing as 22 times the sine of 100 degrees over the sine of 56 degrees. That's equal to B, which is the exact same thing we had previously. So this got it done in one step instead of two. Do you think I care whether you're cross multiplying and then dividing or just multiplying out the bottom? I do not. I will not care. So if you do it in two steps, that's fine. If you do it in one step, that's fine. This one-step process doesn't always work though, because if you need to find an angle, which would be in the bottom, you absolutely have to cross and multiply first, and we will see examples of that sooner than later. Not immediately, but definitely sooner than later. All right. Let's do another example. B. So find all the missing info, same instructions as last time. Angle A is going to be 85 degrees. Angle B is going to be 35 degrees. And then side C, this is a lowercase c, is equal to 30. I am not going to give you radians for these types of problems. It's really only beneficial to use radians when we're talking about the prettier angles like 30, 45, 60, and multiples of those. I'm not saying you can't use radians for something like 10 degrees or 3 degrees or anything like that. It's just not done typically. So if you get confused over whether this C is an angle or a side length, well, hey, look, these have degrees and this doesn't, so that must be a side length. Or your teacher forgot to write the degrees, right? Ha ha ha. But I didn't. So if you want to draw up your triangle, you can. It's not mandatory necessarily. Again, I'm drawing what might look like an equilateral triangle. Please do not interpret it that way. It doesn't matter which one you call angle A. I typically do the bottom left. But again, this is not mandatory. So if I call that the 85 degrees, that means side A has to be opposite of it, which we do not know. So there's our A. Then we have angle B. I could call it the top one, or I could call it the right one. I tend to do B for this one, so let's go 35 degrees on the top. Again, you don't have to. I could have done it in the lower right, which makes the bottom side side B. And then we know that side C is 30. Here's angle C, which means this side over here is 30. And we don't know angle C. So there we go. It's one of the benefits, again, of using the Greek letters. You're not going to confuse your C's, but what you might do is confuse your alphas and your gammas. So make sure that you learn those. Alpha is the fish, gamma is the fish turned sideways. Now, in the last problem, we would have been able to actually use the law of sines to find some information first because we had a completed pair. This time we do not have a completed pair. I gave you angles A and B, but side C. So we cannot use law of sines in this moment. We have to find that third angle first. And I'm going to do the shortcut versions so I can skip the algebra. Angle C, that's uppercase C, is going to be 180 degrees minus 85 degrees minus 35 degrees, which ends up being, what is that, 60. So angle C is 60 degrees. Now we have a completed pair of information. We have the C's. So it would be in our best interest to use these in the law of sines to then find side A and side B. So we're going to use the C's in the law of sines. And it doesn't matter. I don't have to put these on the right side just because in the law they were on the right side. I can put them on the left. So we go 30 over the sine of 60 degrees. That's the C's on top of each other. And then we could attack the A's or the B's first. I'll go in alphabetical order. I'll go after the A's. Side length A, which we don't know, over sine of its angle, which is sine of 85 degrees. I'll do this the longer way and I'll cross multiply first, which will give us 30 times the sine of 85 degrees equals A times the sine of 60 degrees. Again, what are we trying to solve for here? We're trying to solve for the A. So that's the thing we want by itself, which means we got to get rid of the sine of 60, so we can divide both sides by sine of 60 degrees. Now, we can actually analytically say what the sine of 60 degrees is. However, we can't do that with 85, so there's no real point to doing one but not the other, so we're going to stick to our calculators. And again, I apologize for not having my calculator downloaded to show you on the screen, but the inputs shouldn't be too terribly difficult. All right, so that tells us that A, well, I'll write it on the right side, 30 sine of 85 degrees divided by the sine of 60 degrees is our A. And when we punch that in our calculator, again, make sure you close the parentheses for the 85, make sure you close it for the 60. Make sure that you are in degrees, because if you're in radians, you'll get a drastically different answer. And it turns out that A, rounded to 1 decimal again, is going to be 34.5. Again, my default is always rounding to 1 decimal place. Now, I can use the completed A's if I wanted to. Now that I have its angle and its side, I could use that in the law of sines to go back and find the B. But again, this is borrowed information that's been rounded. It's not optimal to use this because this answer is a little off. It could make the next answer a little more off. And then if you keep using rounded answers, it can make things go terrible potentially. That's what we mean by error propagation. So it's in our best interest to use what we had completed at the beginning, which was the C's. So for the next one, we will go, what was that, 30 over sine of 60 degrees equals, so that's the C over the sine of C. Now we want to go after the B's. So side length B over sine of angle B, which was 35 degrees. Again, I'll do the extended version of this. I'll cross multiply. I will typically not do the extended version when we move forward though. So 30 times the sine of 35 degrees, that should be equal to B times the sine of 60 degrees. Again, we're trying to solve for this B. To do so, we divide both sides by the thing next to it, which is the sine of 60 degrees. What I really like about using the same information over and over is the fact that the algebra ends up flowing very identically. We divided by sine of 60, we divided by sine of 60. So we get 30 sine of 35 degrees over the sine of 60 degrees is equal to our B. When we type that in our calculator, making sure that we close the parentheses on the 35, that one is absolutely critical. It's really a good idea to close the parentheses for the 60 as well. It turns out that rounded to 1 decimal place, our B is, dramatic pause, 19.9. Okay, so again, did we have to draw up this triangle? No. This drawing honestly does nothing for the actual math, but it gives us a good visual representation that a lot of people find helpful. We found the extra angle first because it was the easiest thing, and in fact, in this problem, it was mandatory. Again, in example A, we could have found it second, but this time we had to find it first because there was no completed pair. So we found our third angle. Then we used the law of sines to find either A or B, and then the law of sines to find the other one. And the algebra in this law of sines, it's going to be the same thing over and over and over pretty much. There's one other version of this that we'll see, again, sooner than later, where it kicks it up a notch, but it's still nothing insane. So let's do another one. Practice makes perfect, right? C. All right, angle B is going to be 5 degrees, little angle. Angle C is going to be 125 degrees. And then side B is going to be 200. Oops. not degrees, that's a side, not an angle. So we have two angles and a side. This is the angle, angle side, or angle side, angle case. We can go ahead and find the third angle, but if you really wanted to, because we have a completed pair of information, the B's, you could go after side C first. It's just not optimal. So that third angle, which would be A, would be 180 minus angle B, which is 5 degrees, minus angle C, which is 125 degrees. It's 180 minus 130, which is 50 degrees. So A is 50 degrees. I'm not going to drop the triangle this time, just to show you that it doesn't matter. Well, we still have the completed pair of B's, so we can go after the A or the C side length next. I've been going in alphabetical order. I'll be consistent with that. Again, the order doesn't matter. So let's put the B information on one of the sides of law of sines. So 200 over the sine of 5 degrees. That's little b over sine of big B equals, and we're going to attack the A's first. So little a over the sine of angle A, which is 50 degrees. So you could cross multiply and then divide by the sine of 5 degrees. I'm going to take that shortcut this time, and I'm just going to multiply both sides. I wish I'd give myself just a little more room. Multiply both sides by the sine of 50 degrees here. This is the shortcut for this problem. So times sine of 50 degrees times sine of 50 degrees. Sorry for having to squish that in there. Wasn't thinking about it. The reason we do that is because in one step, we will solve for the A. It's just a shorter version. So that tells us that sine of 50 degrees times 200, but it's best to have the 200 first. 200 sine of 50 degrees, order of multiplication never matters, over the sine of 5 degrees. That is equal to side length A. And when you type this into your calculator, the answer might be a little bit unexpected, in fact. So again, make sure you're closing your parentheses, make sure you're in degree mode, make sure that you know how to handle this, because this is an expectation. You'll get that A, rounded to one decimal place, is 1,757.9. A really big number in comparison to the ones we've seen so far. And you might even think that that's unexpected here, but side B is 200, so having one that's about 1,800, that's not completely far-fetched. It's only 9 times larger. And here's what tells me that I should be expecting a really large answer for A and C. Angle B is a teeny tiny angle. This is teeny tiny angle. We've discussed that the smaller the angle, the smaller the side opposite of it. The larger the angle, the larger the side opposite of it. So the smallest angle has to be opposite the smallest side. So because B is this tiny little 5 degrees, it's definitely the smallest angle, 125 versus 50. And that means this 200 is supposed to be the smallest length. 200 is a pretty big number, and it's opposite of a side of 5 degrees. Well, if the 5 degrees is supposed to be teeny, and this 200 is teeny in comparison, and it is small in comparison to about 1,800. So I'd say this answer of 1757.9 does make sense. Okay, now let's find the C. So we'll use the same left-hand side. We're going to continue with the B's. The 200 over the sine of 5 degrees is equal to little c over the sine of big C, which was 125 degrees. Now again, you could cross multiply this and then you'll have to divide by something. I'm going to take the shortcut. Since this is just our variable divided by something, I'm going to multiply both sides by that something, which which is sine of 125 degrees. That way, on the variable side, all that jazz goes away, and it just says C equals. So sine of 125 degrees times 200, let's swap that order, is 200 times the sine of 125 degrees, all divided by the sine of 5 degrees, which is equal to little c. And again, on an analytic test, no calculators, you could have done all this. This would be the answer. This is analytic, it's perfect, it's not rounded. But if you go and type this in a calculator, closing your parentheses, making sure you're in degree mode, it turns out that rounded to the nearest tenth, C is 1,879.7. 1,879.7. And I want to box that up. So we were given our 3 pieces of information. We found the other 3 remaining bits of information using the law of sines. Can you always use the law of sines? No. There are problems that aren't designed this way that has to use something called the law of, you might be able to guess it, cosines. That'll be the next section, and we are not even close to there yet. And again, these are the easiest type of problem, and that might sound a little scary, but these are the easiest because we were given 2 angles and a side. This is by far the easiest type of problem. All right, so with that being said, let's get into the next step up in difficulty. Let's go to, and I need to get out of the whiteboard. What we call the ambiguous case, which is side-side angle. Now, this is not SAS. Side angle side is a very different case than side-side angle. Now, side-side angle would be the same thing as angle side-side, but I think you can probably guess why we don't abbreviate it angle side-side and we go with side-side angle. Use your imagination there and have a good little chuckle. So what this case is means that, again, if you're going either clockwise or counterclockwise, the first thing you see is a side, then the next thing you see rotating is another side, and then an angle. And I'm saying the known information. Side angle side would mean that you see a side, then an angle, then a side in that order. The SAS case, I call that a corner of information. So we'll talk about the SAS case in the next section. Spoilers, it's the law of cosines. And again, for now, we're dealing with side angle. And we call this the ambiguous case because one solution is not guaranteed. It could be no solution or 2 solutions. There can actually be 2 unique triangles under the SSA case when I'm giving you 2 sides and an angle, and the angle given is not between those 2 sides. So I'm going to draw up a picture to explain this after I do all the typing and stuff. The reasoning is why there can be no triangle or 2 triangles, but let's just go ahead and lay out the instructions for now. So first, determine the second angle by the law of sines. You have to have been given a completed pair of information. I have to give you the angle and the side of A, or the angle and side of B, or the angle and side of C. You have to be given a completed pair. So when you're given a completed pair, that means you can use that to find another bit of information with the law of sines. Okay, once we have this, once we have the second angle, let me be consistent with how I'm writing that, second angle, take the supplement of it, which is 180 degrees minus the first. Let me say minus the angle instead of the first, because that might imply the first angle, not the second angle. Okay, so once you found your second angle, you're going to take the supplement of it. Why, again, we'll get to the reasoning in a little bit, but I will give you the reasoning. So the supplement means that 2 angles add to 180. Complement means they add to 90. as a reminder. If, and this is a big if, if the sum of the original first angle and this second version of the second angle sum to under 180 degrees, then a second triangle exists. I know that's a very specific condition. If the sum of the first angle and the supplement of the second angle, when I say second version of the second angle, I mean the supplement of the second angle. The second angle being the thing we found by law of sines. So if the original first angle that was given to you plus the supplement of the second angle you found, if that adds to something under 180 degrees, then a second triangle exists. The basic reasoning here is if a second triangle exists, the supplement of the angle we find by the law of sines is the second version of that angle. As long as those two things add to less than 180 degrees, that means that a third angle can be wedged in. But if these two angles add up to more than 180, that's already not a triangle. How in the world could we have a third angle? So this doesn't have anything to do with the first triangle. It's just determining whether a second triangle exists. Okay, so given a side sided in an angle where the angle is not between the two sides, find a second angle by using your law of sines. Once you have that, take its supplement. If this number that you find after taking a supplement, if you take that and add it to the original given angle, if that's under 180, there is a second triangle, which means there are not 3 answers to be given, there are actually 6 answers. There will be 2 versions of each of the angles and sides that were not prescribed to you. Now, the sides and angles that are prescribed to you, that's it. They don't have second versions. All right, so let's see if we can draw this up and kind of visually explain what's going on here. So our ambiguous case. Which is side, side, angle. Again, that means the angle is not between them. If there's only one triangle, let's call this angle A. I'm going to draw it on the outside this time. Let's call this side A then. They have to be opposite of each other. And then we'll say that the second side given is B, and we'll make it this one. It could have been the bottom one. It doesn't matter. I'm just going to make it the top one. Top left one, excuse me. This is your one triangle case when your A value is in the sweet spot. There's only one possible version of this. If you have no triangle, I gotta draw this just right. There we go. So again, let's make the bottom left angle A, which would make this side A, and then this side, we're going to be consistent and call that our B. So if I give you side A, angle A, and side B, if this side length of A is too small, if this angle is a little too big and this length's a little too small, this is not actually going to be able to reach the bottom, even if you draw it perfectly straight down. So there's kind of a gap here, and this gap is why there is no triangle. It's when the angle A is just too big or side A is just too small. And you could argue that that it also means that side B is way too large in comparison to side A. But this is typically when we have small values of A, but don't just look at the numbers and try and guess this. Your calculator will tell you that this happens, trust me. When we see our examples, well, I'm not gonna be able to show you, unfortunately. I really gotta make sure I download that next time. The 2 triangle case. That is an A in there. 2 triangles. Okay, so that is terrible looking. Let's do that a little straighter. I'll make this go about right here. So here's angle A, here's side B, and then here's side A. So this is visually a case where you could end up with 2 triangles. So the A's and the B's are the information that's given. We're given the 2 sides and one of the angles. So one way of drawing this triangle is to have A go this way, or I'm going to have a different representation of A in red here. What if instead of swinging it to the right, what if we swung it to the left like this? So this red would be an alternative. So this right side wouldn't even be here. So I'm going to show this in 2 different pictures as well as the one. So here's the original triangle I drew first, with the little a here, the big A here, and the little b here. Or, see, I'm not changing B at all. That length is the same. I'm not changing angle A at all. That angle's the same. And I drew that too far. I'm not changing the length of B, I'm not changing angle A, and I'm not changing the length of A either. I'm just swinging it a different way. Oh, that erases entirely too much. What a weird eraser. There we go. So again, just imagine that side A is on a pivot. I could swing this thing to up here, I could swing it over here, but I only want to actually swing it to form a triangle, so I have to connect to this bottom side. So it can swing here and form the wider triangle, or it can swing inside to form a narrower triangle here, a triangle with less area. I can't do that with this one triangle version because A is a little too long. If I swing it back to the left to try and hit this side somewhere, it's never actually going to be able to do that correctly. When A is too short, not only can it not make 2 triangles, it can't even make 1 because of this gap. But this is what most people consider the worst case scenario, when the ratios of A, B, and angle A are all in this perfect sweet spot that you could swing it to the left or to the right, and there's 2 different triangles. Now, we will not get to this case today as an example. It'll be probably the first thing we do next time, but we will see at least something happen here. So let's try another example, or a new example, that is, example 2. We'll go with A. And I'm actually going to do example B first from what I would have originally done, and that's just in the interest of time because we are getting close to the end. Let's say that side length A is 10, side length B is 30, and then angle A is 150 degrees. So side lengths of 10, 30, and 100, and then 150 degrees for the angle A. I can give you A and C, I can give you B and C. It doesn't matter what letters these are. What matters is that you have a completed pair. The A's are completed, and it's only one of the angles given. This is side angle. If you wanted to draw this up, what you think it might look like, so we're postulating that this would be the triangle. If the angle A is 150 degrees, that's here. That means this has to be the side A of 10, and B has to be 30 to be consistent with the drawings before. We'll put the 30 here, but it could be on the bottom. So we're trying to find angle B, which is opposite of 30, angle C, and side C. Well, because I'm only given one of the angles, I can't say 180 minus 2 of the angles is the third because I don't have 2 angles, I only have 1. So we have to use law of sines first. So the completed pair is the A's, so we'll go 10 over the sine of 150 degrees is equal to, well, we have side length B, so we got to use that, 30 over the sine of angle B. Now, this is a different type of proportion than what we saw in example 1A, B, and C. In examples 1A, B, and C, it was the sides, the top values, that had something missing. Now it's the angle that's missing. So we don't have the ability to just solve this in that one step. We have to cross multiply, which is going to give us, let me actually go up here, 10 times the sine of angle B is equal to 30 times the sine of 150 degrees. I forgot my 0. Now again, the thing we're trying to solve for here is this B, but that has the sine of that angle. We cannot divide both sides by 10 sine. We can divide both sides by 10, but we can't just divide by a sine. We'd have to divide by a sine of the value. So this says that the sine, wrong color, of angle B is equal to 30 times the sine of 150 degrees over 10. Now, you can leave this alone, but the 30 and the 10 on top of each other do reduce. Don't try and reduce with the degrees. Degrees and side lengths cannot reduce. You cannot reduce 10 versus 150. You can reduce the 10 and the 30, though. So those are going to be a 3. Again, you don't have to do that because this is all going to get jammed in a calculator anyways. But if you recognize simplifications, go ahead. So sine of B equals 3 times the sine of 150 degrees. Now, back in chapter 5, we said if you ever have a sine of an angle equal to something, in order to solve this, what we do is take the inverse sine of both sides. That was the whole reason we created the inverse trig function, was ultimately to be able to solve trigonometric equations involving a sine of an angle. So we take the inverse sine or arc sine of both sides. Some people don't take this step. Some people will just go ahead and say, all right, if sine of B equals this, then the angle equals the inverse sine of that stuff. I like to show the work, at least at first. So inverse sine of the sine of B. Oops, I forgot to switch my color. Dang it. There we go. Equals inverse sine of 3 sine of 150 degrees. Again, I took the inverse sine of both sides because an inverse sine of a sine cancel each other out. That's how inverse trig functions work. Now you might say, well, Mr. Beckner, you said back in chapter 5 that you have to be careful. You have to make sure that your angles are in the appropriate quadrants. Well, we're talking about triangles. All angles of triangles are between 0 and 180 degrees. And well, that says, okay, well, if it was between 90 and 180, this wouldn't work, but we know angle A is 150, so angles B and C have to be acute. They have to be less than 90. So this is perfectly fine. These two things do, in fact, cancel each other out. So we get angle B is equal to the inverse sine of 3 times the sine of 150 degrees. Now, if you go and type this in your calculator, I'll give you a second and pretend like we're all typing that. What you would end up getting is undefined. Or D&E or whatever your calculator might say. So by calculator, you get that the angle is undefined. Well, the sine of 150 degrees is actually analytic. We can figure that out. The sine of 150 degrees is a half because the sine of 30 degrees is a half, and that's just in quadrant 2. Sines are positive in quadrant 2. So this is the inverse sine of 3 times a half, which is the inverse sine of 3 halves, which is 1.5. 1.5 is outside of the domain of inverse sine. Because the range of sine is from -1 to +1 inclusive, and we even reminded ourselves that last class. So you cannot take the inverse sine of a number bigger than 1. That's why it's undefined. So guess what that means? Because we got an undefined answer, there is no triangle. There is no triangle. So this triangle that I drew up here was not even supposed to be drawn. And that's why I kind of preemptively said that at the beginning. When we draw these by hand, we're not saying that it's going to look exactly like that. We're just kind of giving ourselves a visual representation that may or may not be good enough. So how can you tell when there's no triangle? Your calculator is going to spit out nonsense. But you still have to understand the algebra to get to that point, the algebra and the trig, of course. And on that note, we're going to go ahead and call it a day. We did not finish this section. We did not even come close to finishing this section. We still need to do a couple more examples with this ambiguous case, and some of them are going to be, oh, pardon me, I'm stretching. Some of them are going to be a little bit longer because there's going to be 2 triangles. And again, that's going to be the most complicated case that we're going to see. That aside, like I said, we'll go ahead and call it a day. Please make sure that you are working on your review, working on your test. As I said, the test is a little shorter than the review. I'll take your best grade. Partial credit, I really can't necessarily do anything with that. I can't really count your work because how do I know if you didn't edit your work after you submitted your test? So it's really only very, very, very special situations like you had like a typo or something and you have to let me know in a situation like that. And I have to be able to look at that typo. It's like, oh, you had a decimal in there or something that just shouldn't have been there. Like you were at 3.5.9, I don't know. Or you put in a Z on accident somewhere. So please pay attention when you're working on these. Please be careful. That way you can get the best score possible. Use this as an opportunity. All right. So have a good one. Work hard, get some homework done, and we will see you Wednesday morning on the internet. Have a good day.